Today we are talking about one-sided limits and finding the limit given the graph of a function. We've been talking about limits in this class for a long time. We first saw a limit back in Unit 1, way back in August. So it is important to know that limits are it's the backbone of all that we do in calculus. It opened huge doors for tremendous advancements. So I'll let you read about that. So we are going to begin by talking about one-sided limits. So a one-sided limit, and we've already done this, but we're going to formally talk about it today. We are approaching an x value from only the left or the right side of that x value, and that's called a one-sided limit. We use this notation for it. This notation here, limit as x approaches 5 from the left. That's how I would read that. Of f of x. First of all, you guys, it is very tempting to write this part of the limit and not write this part of the limit. This is crucial. You have to write something here. This is always where your function goes. If you're given the graph of 3 functions, you have to know what you're taking the limit of. We are taking the limit of, in this case, f of x. Okay? So x is approaching 5, but only on the left of 5, of f of x. And we want to find out, what is the y value approaching? It is the value that f is approaching as x gets very, very close to 5 on the left of 5. Very, very, very close to 5, but on the left of 5. This notation is it's the limit for x approaching 5 on the right side of 5 of the function. So we will get the function value. It'll be the value of y that is being approached as x gets very, very, very close to 5, but on the right of 5, like this value. Okay? Now, an overall limit, not one-sided, just the limit as x approaches 2 in this case. The limit as x approaches 2 of f of x is equal to 9 means as x approaches 2, both from the left and the right, the value of f approaches 9. Okay? The answer to a limit is always the y coordinate that is being approached. Okay? So this means that the limit from the left is equal to the limit from the right. If the limit as x approaches, say, 3 from the left of f of x is 6, and the limit as x approaches 3 from the right of f of x is also 6, then we say that the overall limit as x approaches 3 of f of x is 6, the overall limit. This is true even if there's a hole in the graph at that point, 3, 6. So it doesn't matter that there's a hole there. Or there may not be a hole, but just saying that the limit exists means that from the left it's equal to the same number as from the right. Okay? Alright, let's take a look at this example. What is the limit as x approaches 1 from the left of g? Here's the graph of g. X is approaching 1 from the left. X is approaching 1 from the left. Where is our curve? Our curve is up here. And what is the y value that we are approaching? What is being approached? If I plugged in 0.999999999, what would be the y value? Probably 6.999999999, right? So that limit is 7. Okay? What about on the other side? Let me get another color here. What about the limit as x approaches 1 from the right of g of x? Well, if we're approaching 1 from the right, it's like we're putting in 1.0000001. What is the y-coordinate approaching? What is the y-coordinate approaching? Well, the y-coordinate would probably be another 6.999999999, right? It is still approaching 7. The limit from the left is equal to the limit from the right. In fact, let's write that down. The limit from the left of g of x is equal to the limit from the right. Therefore, the overall limit is that value. Okay? Alrighty, let's do another one. Let's approach -2 from the left. -2 from the left. Well, here we are, x is approaching -2 from the left. What is the y-coordinate approaching? Well, the y-coordinate is approaching 0. The y-coordinate is approaching 0, right? That limit is 0. What about on the other side? -2 on the right. Well, -2 on the right. Here's x approaching -2. What is y approaching? Y is approaching 4. It's coming from above 4, like 4.000000001, but it is approaching 4. So we say that that limit is 4. In this case, the limit as x approaches -2 from the left of g of x is not equal to the limit as x approaches -2 from the right of g of x. Therefore, we say that the overall limit is non-existent. It does not exist. We abbreviate that DNE, does not exist. All right? So, it does not matter where the actual value of g is. In this case, the actual value of g at x, g of -2 is 0, right? G of -2 is 0. Doesn't matter. It does not matter for a limit. It matters for continuity, which we will be talking about later on in this unit, but it does not matter for the limit. Here, for our first problem, we got the overall limit to be 7. It did not matter where the point was. G of 1 is 2, but that does not matter when it comes to the limit. Okay? All right, let's do another one. Some examples here. Okay, this is the graph of f. Which of the following statements is true? Okay. The limit as x approaches 2 from the left of f of x is equal to f of 2. Well, let's go find f of 2 first. F of 2. There's when x is 2. Here's the function value right here. That is -1. So here x is approaching 2 on the left. 2 on the left. What is y getting closer and closer and closer to? It is getting closer to -1. It would be about -0.9999999, but it is approaching -1, so the limit is -1. That is a true statement. Let's go to another one. The limit as x approaches 6 from the left of f is equal to the limit as x approaches 6 from the right of f. Is that true? Here we are approaching 6 on the left. Here we are approaching 6 on the right. They are both approaching -1. So that is a true statement. They are both equal. Okay, the limit as x approaches 6, the overall limit. Well, we just showed that both of the one-sided limits were -1, so this limit is -1 here. Is that equal to f of 6? What is f of 6? f of 6 is negative 3. Those two are not equal. That is a false statement. So which of the following are true? We want 1 and 2, so C. Next up, the graph of f here is shown. For which of the following values of C does the limit as x approaches C of the function equal 1? So this tells me that the C is an x value that is being approached. It's not one-sided, so that means both sides must come to 1. Both sides must go to 1, right? So let's take a look here. I'm kind of looking at where y is 1, because remember, this is a y value. So I'm looking at where y is 1. And y is 1 right there where I drew that dashed line, right? So where is the limit from the left equal to the limit from the right? And they're both equal to 1. Well, right here, the limit from the left and the limit from the left and the limit from the right are both 1. So x equals negative 2 is one such value. Okay, what about this one right here? The limit from the left is equal to the limit from the right. Therefore, the overall limit is 1. That is at x is equal to 0. And then there's one more interesting value over here. Trying to find another color here. We'll get, I don't know, red, I guess. Need to get some new colors here. Okay, this right here. The limit from the left is 1, but the limit from the right is not 1. This is a jump. A jump is when the limit from the left is not equal to the limit from the right. That is a jump. So not x is equal to 3. The only two values are negative 2 and 0, so C. Okay. While we're talking, you guys, well, I see this graph right here. This is called a jump in the graph. It's made by a piecewise function. This is called a hole. A hole is when the limit from the left is not equal to the limit from the right. But the function value either does not exist or it's somewhere else. This right here is not a hole, it's not a jump, it's just continuous. Okay? This is a hole, this is not a hole, this is a jump. Alright, another one. For what values of a does the limit as x approaches a equal 0? So very similar to the last one we did. Here's where y is 0. And we want for the limit from the left to equal the limit from the right. And we want them both to be 0. Right here is a jump. The limit from the left is 0, but the limit from the right is negative 1. So not x is equal to 0. Right here, the limit from the left is negative 1. The limit from the right is also negative 1, not 0. That limit would be negative 1, not 0. Right here, the limit from the left is 0. The limit from the right is 0. We finally have a value of x where it will work. Right here, the limit from the left is 0. The limit from the right is 0. We have another value, and that's it. 2 and 4 only. So guys, jump at x equals 0, hole when x is equal to 1, continuous at 2, hole when x is equal to 4. Okay? Alright, number 4. For which of the following does the limit as x approaches 4 exist? That means that the limit as x approaches 4 from the left of the function is equal to the limit as x approaches 4 from the right of the function. We'll write here, limit from the left equals limit from the right. They are equal. It does not matter at all that that point is up there, at all. Here the limit from the left is equal to the limit from the right, so that also exists. Okay? In this one, they did not define f of 4. In this one, they defined f of 4. But in both cases, we have a hole. It does not matter that that value of the function was elsewhere or non-existent. Does not matter. Here, the limit as x approaches 4 from the left is not equal to the limit as x approaches 4 from the right. This is a jump, so we will not include that one because those two limits are not equal. So 1 and 2 only. Okay? Alrighty. Let's talk about limits at infinity. These are limits as x approaches infinity, and we have been doing this for quite a while. This is where we started way back early, in Unit 1 or 2. Alrighty. If the limit as x approaches infinity of a function is a finite number, then f has a horizontal asymptote of y equals that finite number. If the limit as x approaches negative infinity of a function is a finite number, then that is another horizontal asymptote, y equals k. I made this piecewise function on Desmos, it looks like. Okay, as x approaches infinity, what does it appear that y is getting closer and closer and closer to as x goes to infinity? As x goes to infinity, this function appears to be approaching a y value of 2. So the limit as x approaches infinity is 2. What about as x approaches negative infinity? As x approaches negative infinity, what does it appear that the y values are getting closer and closer and closer to? 0. Therefore, f has horizontal asymptotes of y equals 2 and y equals 0. Okay? Number 5. If the limit as x approaches infinity of g is negative 7, and the limit as x approaches negative infinity of g is 5, which of the following must be true? G must have horizontal asymptotes of both y equals 7 and y equals 5. C. You guys, I got this from AP Classroom. Okay. Alrighty. Leave that up there. Alright, if f satisfies the limit as x approaches infinity of f is 1, which of the following could be the graph of f? Well, if this is true, then I know that there must be a horizontal asymptote of y equals 1. So that's what I'm going to be looking for. I'm going to be looking for a horizontal asymptote of y equals 1. And I'm saying because, gosh, I'm looking at, oh gosh, sorry. I am looking at this. Do I see two of these? What's going on? Oh, I see now. No, I see. X is only approaching positive infinity. X is only going to positive infinity, okay? And as x goes to positive infinity, we must have a horizontal asymptote of 1. So not this one. This one looks like it could be going to 0. This one looks like it is my answer, because as x goes to positive infinity, the y-coordinate is approaching 1. This is the one that I was looking at, but in this one, as x goes to positive infinity, it does not look like y is approaching 1. As x goes to negative infinity, the y values are approaching 1, but not positive infinity, and this said positive infinity. So B. Alrighty? Okay. Limits of infinity. So what happens if if a is a finite number and the limit as x approaches a of f is infinity? A from the left is positive or negative infinity. That means we have a vertical asymptote. Think about what that would look like, you guys. If this is a, and as x approaches a from the left, it's infinity. That happens at a vertical asymptote. Okay? Or negative infinity, it says. So either one would create a vertical asymptote. Or if we're approaching a from the right, a from the right, a from the right. Okay? So if you get infinity as x approaches a number, a finite number, then you're at a vertical asymptote. If either one-sided limit is infinity, the vertical has a vertical asymptote. Okay? Here's another way to write it. All right. Limits of infinity. When you get infinity for the answer, it is a special case of a non-existence for a limit. A does not exist, a DNE. Okay, it's just a special case of it. If I asked you what the shape is, you would probably say it's a square. But it is also true that this is a rectangle, but you probably wouldn't say that's a rectangle. This is also a quadrilateral, but you probably wouldn't say it's a quadrilateral. You would say it's a square. I ask you what shape that is, you would probably say it's a square, because a square is the more precise term when describing that shape, right? Even though it is a quadrilateral and a rectangle, you would say square because it's the most descriptive, right? It is best to be descriptive as possible, okay? In the same way, it is preferable to write infinity or negative infinity instead of non-existent when they are true. So if you get an answer that is infinity, while it's true that it is non-existent, I still want you to say infinity, just like I would still want you to call this a square and not a quadrilateral. Okay, be as descriptive as possible. So to recap this, which of the following is true or false? Or just put true or false. The limit as x approaches 1 from the left is negative infinity. 1 from the left is negative infinity. That is true. Can we also say that the limit as x approaches 1 from the left of f is non-existent? That is technically true. Which is preferable? This way. What about 1 from the right? 1 from the right is indeed going to infinity. Yes, that is true. Can we also say that that is a DNE or non-existent? Yes, that is technically true, but this way is preferable. Okay? All right. Which of the following is true? The limit as x approaches 3 is infinity. The limit as x approaches 3 is infinity. You guys, an overall limit An overall limit can never be infinity. It can never be infinity. Overall limit cannot be. I'm trying to think, as I'm saying that, I'm trying to think of any possible ways where it would be, and it just cannot. That is impossible. Okay? It also cannot be negative infinity. An overall limit cannot be positive or negative infinity. A one-sided limit can, though. So 3 from the left is positive infinity. 3 from the right is positive infinity, or 3 from the left is positive infinity. Which one is the positive infinity? It is the 3 from the right. 3 from the right is positive infinity. Okay, even if one-sided limit is infinity or negative infinity, the overall limit is non-existent. You never say that the overall limit is infinity, okay? Because even if one side is infinity, the overall limit does not exist. Okay, we're getting there, guys. Hang with me. Okay. Which of the following statements is false? The limit as x approaches 2 from the left is infinity. 2 from the left is infinity. That is true. We want it to be false. 2 from the right is infinity. 2 from the right is also infinity. That is true. We wanted false, so I'm not going to call that my answer. The limit as x approaches 2 is infinity. An overall limit can never be infinity. That is false. So that is my answer. So even though both sides are going to infinity, the overall limit is only non-existent. There are a few reasons for that. For right now, you can just think of infinity can have different magnitudes, and I would never say that this infinity is equal to that infinity. Okay? So just go with that for now. Alrighty? Okay. Some common confusions that I would like to reinforce with you. These are things that kids just tend to mess up. So, okay. A whole. A whole is when this is true. The overall limit exists, but is not equal to the value of the function. The overall limit, which means the limit from the left and the limit from the right, are the same. They are the same, but whatever value it is not equal to the function value. So this is a whole. Limit from the left equals limit from the right. This is not a whole. This is called a jump, not a whole. The limit from the left is not equal to the limit from the right. Kids like to think that this is a whole because of this little guy right there, and it's not. A whole must be when the limit from the left is equal to the limit from the right, but not the value of the function. Okay? This is a whole because the limit from the left is equal to the limit from the right, but they are different from the value of the function, which in this case is not even given to us. In this case it was, but it just didn't match up. If it matched up, it would not be a whole. It would just be a continuous curve. Okay, so at what value or values of x does this function have a whole? I see a whole when x is 4. I see a whole when x is 6. Okay, not here, not there. This is a jump. limit from the left is not equal to the limit from the right. A whole is when the limit from the left equals limit from the right. Limit from the left equals limit from the right. These are the only two x values where there's a whole in this graph. Okay, I think that's it. Let me make sure there's no more on, nope, that's the next notes. Alrighty, that's all I got for you for today. 30 minutes. Okay, that was not too bad.